Hi, this is Dan Bullard, retired electronics engineer, sitting out on the front deck of my houseboat again. It's getting close to Halloween. We did see the Boo Boat. We see it every weekend before Halloween. I want to talk about testing a MEMS accelerometer. It measures the orientation of your phone, and it can measure the acceleration or deceleration of your car to know when to deploy the airbags. And so when you have a picture on your phone and you turn your phone 90 degrees, it's that time of year. It knows which way your phone's oriented. That's an accelerometer. And years ago when I was working for Next Test, we went to visit Analog Devices, and my sales guy wanted to get me introduced into MEMS testing. And so we met with this guy, and he said to the we're new to mixed signal. We don't know if we really know what we're talking about. Like, thanks a lot, Marty. So he let me take over, and I did my demo, and the guy turns to Marty and says, I think you know what you're talking about. They gave me some chips, and I went and did this accelerometer. It's really cool. I mean, one thing I did, I clamped it in the hacksaw blade and put it in a vise and let it oscillate back and forth, and it made a sine wave. What a shock. So it's very cool. But of course they didn't want me playing with it, they wanted me to test it. So I tested it. I wrote a test program for it. Now they were testing it on an Analog Devices custom-made tester, and I was testing on the Nexus Lightning. And the Nexus Lightning was a lot cheaper than their homebrew system. But you know, they weren't expecting a lot. But and what they're doing is very cool. Okay, the way accelerometer works is it's MEMS, so it's a mechanical system built on silicon. And so they have a little arm, and the arm is what senses the direction. And so if you hold it this way, it's just hanging there. But if you move it back and forth, it will distort the arm, it'll move the arm, it'll bend the arm. But the cool thing is, the arm is very stiff, it's silicon, and so they don't break, not easily. It can take like 700 G's or something. It's friggin' incredible. But the thing was, there were two of them, an X and Y, so there's two of them. They're 90 degrees, of course. And so with that, you can tell which way your phone's oriented or your car is oriented. If you're upside down, it knows to deploy the airbags on the side, you know, stuff like that. And I always dream about writing an app for a phone where if you drop it, right, if you drop the phone, the accelerometers will sense you're in 0G, right? And so it's falling. And so the phone can, you know, do something like yell and say, ah, help me, I'm falling, whatever. And when it hits the ground, it can go, ouch, depending on how much force it impacts the ground with. You can have it say ouch or ow or I'm dead, you know, whatever. So it's pretty cool. Now what they were doing was they used an electrostatic force to move the beam. And so that's one way they could test it. And those pins are not used during application, but in the testing, they use it to distort the beam so they could test it. And one of the things they did was they applied, same as I did in my periodic white noise test for filters, they applied a white noise signal to the electrostatic beam manipulation, and so it would move the beam in a random fashion using a random number generator. So it's really cool. And then what they were looking for is how much is the beam moving? How fast does it move? Where does it move the fastest? And so that will tell you if the length, how long the beam is, and if the length is right, and if it's not long enough, or if it's too long, you can throw that one away. But once they know what the beam length is, they can put that into the calibration in the EEPROM inside the accelerometer, and they'll know exactly how many G's that thing will take. So it's really cool. That's how they calibrate it. Now, this random number generator generated this periodic white noise signal in just a narrow band. So if it was outside the band, that didn't work. They failed it. But normally it'd be inside the band, and then they look for the peak. And so here's some plots of what we did. We used the AWG to drive the pins that drove the electrostatic signals that distorted the beam, moved the beam, and so we got to see with the ACP, the analog capture instrument, how much that beam was moving. Did an FFT on it. That's how you do it. You do an FFT, and we saw the resonance of the beam. But not just that. We decided, okay, it's kind of a rough looking signal, and that's because we're using noise. We're using periodic white noise. So what we did was we noise shaped it, and then we smoothed it, and it really came out nice. So it told us exactly where the center was, and from that they could work out how long the beam is and what the calibration values were. The cool thing about this was our tester, the next test, Lightning, tested it in 1/4 the time it took their analog devices tester to test it. So the analog devices homebrew tester took 4 times longer than the next test Lightning. So that was a real boon. So what that would mean is that we could test 4 chips in the same time that they would test 1 chip. And we could do multi-site. I don't know if they could do multi-site, but we could do multi-site. So we could test 4 chips. They could test 1 device. We could test 4 devices in the same time. And they really, really wanted that tester. Bob Malone, the manager there, really wanted it, but Analog Devices said, no, you can't have it. So Bob Malone quit. So that's what happens when companies make bad decisions. So it's pretty cool though. That's a MEMS chip. Those are in your phone, so you know what the phone is doing. When you turn it 90 degrees, it knows which way it's facing, and that's MEMS. That's kind of a new thing. It's way more sophisticated than some other parts that I tested. So MEMS is cool. You can have a good time with MEMS, and you need an FFT. You need to do an FFT. So please, for God's sake, learn how an FFT works. Okay, so once again from the river, this is Dan Bullard.